So I was discussing about normal reaction. I'll take one more question to discuss this normal reaction. Suppose we have these two masses, say this is 10 kg and this 5 kg. I skipped on this platform, I skipped on this floor, and suppose the whole system is moving downward. We say the velocity, the acceleration 2 meters per second, and the question is, we find the normal reaction at the interface of these two blocks and normal reaction between 10 kg block and the earth and the ground. So we have to find the normal reaction at these 2 points. That's the question. We have two blocks, one is having mass 10 kg, other is having mass 5 kg, and the whole system is moving downward with 2 meters per second square acceleration, and we have to find the normal reaction at the interface of 5 kg block and 10 kg block, and normal reaction at the interface of this ground and 10 kg. We have to find normal reaction as these two surfaces. So first thing we have to do is we have to draw the free body diagram. I'll draw the free body diagram of 5 kg and I'll draw the free body diagram of 10 kg mass. So let's draw the free body diagram. Alright. This is 10 kg body and this is 5 kg body. You first show all the forces. Please show all the forces acting on these bodies. Please also all the forces acting on these bodies. In order to understand the forces, you first see with what to what object this 5 kg is interacting, and how does this 10 kg interacting with the surrounding. This 5 kg is interacting with the earth. So you have gravitational force 5g. This 5 kg body is interacting with the earth, and earth exerts 5g on this body in downward direction. We assume that earth is in downward direction. Earth pulls every body with the force equal to its weight. So it is interacting with the earth. So that interaction is being shown as 5g. Alright. What else it is interacting with? It is interacting with 10 kg mass. See, if this mass would have been free, if the body would have been free, the body would have accelerated at the rate of 9.8 meters per second square. But the body is going down with 2 meters per second square. It means the motion of this body is constrained. Had it been free, it could have gone down at the rate of 9.8 meters per second square. Under the effect of this 5g, this body could have accelerated in downward direction with 9.8 meters per second square. But this is going down with just 2 meters per second square. It means the motion is constrained in downward direction. And who is constraining it? It is 10 kg mass who is constraining the motion of 5 kg mass. And how it constrains it? By applying a normal reaction in direction opposite to the direction which motion is constrained. So that's N1. Alright. So 10 kg mass is applying force on 5 kg mass, that is N1. By applying this normal reaction N1, it is constraining the motion of 5 kg mass. Alright. Now, who applies this N1? It is 10 kg which is applying N1. And as a reaction, if I call it action of 10 kg on 5 kg mass, then 5 kg mass is going to apply a reaction force, and that will be equal and opposite. 10 kg apply N1 on 5 kg mass, so 5 kg mass will apply a reaction N1 in opposite direction and equal in magnitude. So 10 kg will apply N1 force on, 5 kg mass will apply N1 force on 10 kg mass in opposite direction. What else 10 kg interacting with? 10 kg is interacting with the earth, so we have a force of 10g. It also interacts with the surfaces. They interact with the surface. See, had this 10 kg been free, it would have gone down with acceleration of more than 9.8 meters per second square, because net force in downward direction is 10g and n, 10g plus n1. Had it been free, it could have gone down with that acceleration of more than 9.8 meters per second square. But we are finding that this body is going down with 2 meters per second square. It means what? The surface is constraining the motion of 10 kg mass by applying a force let's call it N2. The surface is constraining the motion of 10 kg mass by applying this force N2, and as a reaction 10 kg mass will apply force N2 on the surface. So each of these forces is telling you about the different kind of interaction the body is subjected to. This 10 kg body is interacting with 5 kg, so you have N1 for that. This 10 kg interacting with the ground, so you have N2 for that. This 10 kg mass is interacting with the earth, gravitational force, which is field force, that's why you have 10G, right? That is 10G. So this is the free body diagram, and you know that both are accelerating with 2 meters per second square. So we can apply Newton's second law, that is, you have the net acceleration in 2 meters per second square in downward direction. So what is net force in downward direction? That is 5G minus N1 equal to 5A. That is 5 into 2, and this is net force in downward direction comes to be, since the acceleration lies in downward direction, so net force will also lie in downward direction. So net force in downward direction is 10G is 10 into 2. So from here I can say N1 is 40 Newton, and from here I can say if it is 40, 140 minus 20 is 120, so this is going to be, I think it is 120 Newton. N2 is 120 Newton. So this is normal reaction. This is the normal reaction. This is going to be your normal reaction. Now suppose in the same problem, if I keep a body of say mass 3 kg, and now I ask you, you just tell me what is the normal reaction acting on these three interfaces, right? How will you do that? I'll proceed in very similar fashion. I'll have one more body of 3 kg, right? This 3 kg interacting with the earth, so you have 3G. This 3 kg also interacting with 5 kg, and 5 kg is constraining the motion of 3 kg mass, because had it been free it could have gone down at an acceleration of 2 meters per second square, sorry, at the acceleration of 9.8 meters per second square, but since it is going down with 2 meters per second square only, so 5 kg mass must have been applying a force, say N3 on 3 kg mass. And who is applying this N3? It is 5 kg which is applying N3. So 3 kg will apply a reaction force on 5 kg N3, right? This N3. See, all of them are going to interact with the earth, because earth does not need the bodies to be in contact with it for gravitational force. The gravitational force is a field force. The normal reactions is characterizing the contact force. It is contact force. So since 10 kg mass is under the contact with the surface, so surface will be interacting with 10 kg mass only. Surface will be interacting with 10 kg mass only. It is 10 kg which is interacting with 5 kg. It is 5 kg interacting with that 3 kg, right? But you do have impact of 3 kg on the interaction of the surface with 10 kg. You'll find that when I put this 3 kg, you'll find that a normal reaction at this interface will change. So 3 kg do have a significance over here. 3 kg, by putting 3 kg, you will find that the force of interaction between 10 kg and the surface is going to increase. You will find increase in N2, right? So you will see that. But then 3 kg is not directly interacting with 10 kg in fact. But it do have an impact, right? But since it is not interacting, I have not shown any force between 10 kg and 3 kg. 3 kg interact with 5 kg, and that interaction will affect the interaction between 10 kg and the surface. You will see that. You will see the difference in answer. So let me think if there is any other change. 5 kg interacting with 3 kg, so we have a force N3. 5 kg interacting with the earth, so you have 5G. 5 kg interacting with the 10 kg, so we have force N1, which 10 kg applying, and as a reaction 5 kg applying force N1 on 10 kg. 10 kg interact with the earth, so you have 10G. It interact with the surface also, so it has got N2 force. Okay, fine. See, I must make it very clear. Suppose you have an earth over here and you have a mass M. Regardless of the fact that this mass M is on the surface or it is away from the surface, you always have this force mg. But the moment it comes on the surface, now you have two forces. One, the gravitational force which Earth is exerting on it, and other, a normal reaction, because now the Earth is also constrain the motion of this mass. So you have a normal reaction between Earth and the mass. So when it is in the air, you have just mg only, you don't have a normal reaction. But when it comes on the surface, you have a normal reaction also. And remember, this N and mg are not action reaction forces. I must tell you that if Earth apply mg on this mass also apply mg on the Earth, and these are action reaction forces. If Earth apply normal reaction N on the body, this body also apply N on the surface on the Earth, and these two are action reaction forces. If this Earth is applying N force on the body of mass m, this body also apply a force N on the surface, that is action reaction forces. You should not confuse that N and mg are the action reaction forces. It is not. Earth apply mg on the block also apply mg on the Earth. They are action reaction forces. Here Earth apply N, if this mass comes in contact with the Earth is also constrain the motion of this mass towards the center, right? Because mg is acting, the mass would have moved, but the motion is constrained. That's why Earth is also applying N when it comes in the contact. And when Earth apply N, this mass also apply N on the Earth, right? So they are the action reaction forces. You must be very clear about it. Okay, let me see this question. So you have one equation here, 3g minus n3 is 3 into 2, and now this equation will get modified. I'll modify this equation. This equation will come as 5 into 2, and here the equation will remain same. Okay, here the equation is going to remain same. So this n3 is going to be 24 Newton, and now this n3 is 24 Newton. So n1 comes to be how much? 24 plus 50, 74, 64 Newton. Okay, and n2 will come as 100 plus 64, 164 minus 20, 144 Newton. Please check it, right? Please check these values. So you find that the normal reaction, the force of interaction in 10 kg and the surface increases to 144 Newton. Earlier it was 120. So that's the impact of 3 kg on this interaction, right? I directly can't show in the free body diagram, but that's how the presence of this 3 kg affect the interaction, right? If I remove this 3 kg, again your N2 becomes 120 Newton. All right. So that's the question on normal reaction. Now in the same problem, I'll do some manipulation over here. I'll do some manipulation in the same question. Let me do it. Suppose instead of putting these masses one on the other, let me put. Suppose you have these three masses.
10 kg. This is 5 kg. And this is 3 kg. And I have a force, say 90 Newton, 18 Newton. So these are the forces, 90 Newton and 18 Newton. And I have to find what is the normal reaction or the contact force at the interface of 10 kg and 5 kg and 5 kg and 3 kg. Alright. So for that, let me draw the free body diagram. Let me draw the free body diagram. This is say 10 kg body, and let's say this is 5 kg and this is 3 kg. First of all, you saw all the forces which you think is quite obvious. So like gravity is always there. Gravity is always there. So I'll put 10g. Here I put 5g. I put 2g. And their reactions also. N1, N2, N3.
What else you see? You see this force 90 Newton acting on this body, and you see 18 Newton acting on this body, right? So these are some of the forces which we can see very easily. Like mg is always there, and since all this body, the motion is constrained in downward direction, so you have the normal reactions. You have 90 Newton, which is quite visible. You have 18 Newton. Now, if this body would have been free, what would have been the acceleration? It could have moved with 9 meters per second square. But this body is not free to move towards right. You have 5 kg in front of it. You have the 5 kg in front of it, right? So 5 kg, the presence of 5 kg in front of this 10 kg will constrain the motion of 10 kg mass. Right? So, like suppose if you are walking in certain direction and you have very strong wind coming from this direction, your motion is constrained. Or if there is a water and you are swimming in the water, right, then your motion is constrained by the presence of water. Air does not constrain your motion so much, still air, compared to water. Water constrains your motion more. If you are in the air, you are walking in the air on the surface, the presence of air do not constrain the motion so much as the water constrain your motion. Water constrains your motion more. It's difficult to swim a distance of 1 meter compared to moving in air at over a distance of 1 meter. So here the motion is constrained, right? Water exerts a force N on us in opposite direction. Similarly, if I give 5 kg mass in front of 10 kg mass, I am pushing this mass from towards right, and I have got 5 kg in front of it. Had this been free, the motion would have been unconstrained in towards right, horizontal motion. But presence of 5 kg mass does constrain the motion of 10 kg mass. And in which direction it is constraining? It is constraining the motion towards right. So the motion is constrained towards right. So you have a normal reaction, say R1 towards left. By applying this force R1, 5 kg is constraining the motion of 10 kg mass. And as a reaction, this 10 kg mass is going to apply force R1 on 5 kg mass. Now, under the effect of this R1, had this body been free, it would have accelerated freely at the rate of R1 by 5 meters per second square. But the presence of 3 kg mass will constrain the motion of 5 kg mass also. 5 kg mass is also not free to move towards right. You have 3 kg. But see, if you put any mass in front of any body, obviously the motion of that body will be constrained in that direction. So 3 kg mass is also constraining the motion of 5 kg mass towards right. So it will be exerting a normal reaction R2 or a contact force R2. By exerting this R2 force on 5 kg mass, this 3 kg mass is constraining the motion of 5 kg mass. So if I treat it as axial of 3 kg and 5 kg, then 5 kg is going to apply a reaction force R2 towards right. The action and reaction pair must be equal and opposite, right? So you have this scenario. Fine. Now suppose A is the acceleration of these 3 bodies towards right. You can easily find A by taking it as one system of 18 kg and net force 90 minus 18, that is 72. You can take it as one system, say it is 18 kg the whole system, and with net force 90 minus 18 Newton, that is 72 Newton. So acceleration will be 4 meters per second square. In short, you can do that. But I can do it in this way also. I can write the free body. I have drawn the free body diagram. I can write the equation of motion. Say this 3 kg has got no motion in vertical direction. So N3 minus 2g is 0. Similarly, this 5 kg do not have any motion in vertical direction. So N2 minus 5g is 0. Here N1 minus 10g is 0. Now the net force towards right is going to be R2 minus 18, and that's equal to 3a. Net force here is R1 minus R2, and that's equal to 5a. And net force here is 90 minus R1, and that's 10a, right? So from these 3 equations you get N1 equal to 10g, N2 equal to 5g, and N3 equal to 2g. So from here, if I call it equation number 1, equation number 2 and equation number 3, and I add all the three equations, this R1 R2 will cancel out. If you add 1, 2 and 3, you get A equal to 4 meter per second square. And if I put all these values, if I put this 4 meter per second square over here, what's R2? R2 is 12 plus 18, that is 30 Newton. If I put A over here, R1 is going to be 50 Newton, right? R1 is going to be 50 Newton. So these are the forces acting on these three masses. So that's our normal reaction. That is all about normal reaction. Normal reaction acts in direction opposite to the direction which motion is constrained.